Hello and welcome to another episode of Maths Whenever. In this video, we're going to look at three of Archimedes' mathematical achievements. We'll do so using the modern mathematical notation of algebra, geometry, and calculus, which will be much easier to understand than Archimedes' original geometrical proofs. First, we will look at what he considered his proudest achievement, that of the ratio of the volume of a sphere to that of a circumscribed cylinder. The second will be how he narrowed down the elusive value of pi using inscribed and circumscribed polygons. The third and final one will be how he found the area of a parabolic segment. Archimedes made other important mathematical discoveries, such as the area of a circle and an ellipse, as well as the surface area and volume of a sphere, each of which were brilliant. Archimedes was an ancient Greek mathematician and physicist who lived in the city of Syracuse on the east coast of Sicily in the 3rd century BC. He is considered to be one of the greatest mathematicians of the ancient world and indeed of all time, along with the Englishman Isaac Newton, the Swiss Leonhard Euler, and the German Carl Friedrich Gauss. The earliest recorded historical references to Archimedes come from the ancient Greek historian Polybius in the 2nd century BC, the ancient Roman historian Livy in the 1st century BC and AD, and then Plutarch in the 1st and 2nd centuries AD. Let's begin with his proudest achievement first. Consider a sphere with radius r inside a cylinder with the same radius as the sphere and the same height. He proved that the volume of a sphere is 2/3 the volume of the circumscribed cylinder. He also proved that the surface area of a sphere is 2/3 the surface area of the circumscribed cylinder. Fortunately, using our modern mathematical notation, this is very easy to prove. But first, we must know the formulas for the volumes and surface areas of these shapes. We can thank Archimedes for these formulas. Here is a sphere with radius r inscribed in a cylinder. The formula for the volume of a sphere is 4/3 pi r cubed. And the formula for the volume of a cylinder is pi r squared h. Putting these formulas into a fraction with the volume of the sphere in the numerator and the volume of the cylinder in the denominator, we get the following. Now, since the height of the cylinder is twice the radius, we can make this substitution, giving us the following fraction. Expanding the brackets in the denominator then produces 2 pi r cubed. Here we can immediately see that the pi r cubed in the numerator and denominator cancel, leaving us with 4/3 divided by 2. This can be rewritten as a division of the two fractions as follows. Then as a multiplication of two fractions as this. Multiplying these two fractions yields 4 divided by 6, which then simplifies to 2/3, Archimedes' cherished result. Archimedes was most proud of this result and wanted it inscribed on his tomb. Interestingly, he also proved that the surface area of a sphere is also 2/3 the surface area of the circumscribed cylinder. This can also be shown to be the case as follows. Archimedes also worked out the formulas for the surface area of a sphere and a cylinder. The surface area of a sphere is 4 pi r squared, and the surface area of a cylinder is 2 pi r squared plus 2 pi r h. As a ratio, this is 4 pi r squared divided by 2 pi r squared plus 2 pi r h. Again, since the height of the cylinder is twice the radius, we can make this substitution, which gives us the following. Expanding the brackets in the denominator then produces the following. Combining the like terms in the denominator, we then get 4 pi r squared divided by 6 pi r squared. Again, we can see that the pi r squared factors in the numerator and denominator both cancel, leaving us with 4 divided by 6. This, of course, again simplifies to 2/3. Archimedes died during the Roman capture of Syracuse, killed by a Roman soldier, even though it was ordered that his life should be spared. During the 1st century BC, the Roman statesman Cicero was serving as a public official in Syracuse. While he was there, he found Archimedes' tomb and is said to have restored it. Archimedes and his discovery of this ratio are shown on the highest award a mathematician can receive, the Fields Medal, sometimes described as the Nobel Prize of Mathematics. The award is named after the Canadian mathematician John Charles Fields, who proposed its creation, provided the funds and championed its establishment. Unlike the Nobel Prizes, which are awarded annually, the Fields Medal is awarded every 4 years. The front of the medal shows an image of Archimedes with his name written in Greek. The text in Latin translates to surpass one's understanding and master the world. The reverse side shows the image of a sphere inscribed in a cylinder behind an olive branch and a text in Latin which translates to mathematicians gathered from the entire world have awarded this prize for outstanding writings. Let's now look at how Archimedes narrowed down that elusive number we now call pi. Recall that pi is simply the ratio of the length of a circle's circumference to that of its diameter. Today, we now know that this ratio cannot be expressed as a ratio of two whole numbers. But Archimedes did not know this. No wonder he went through so much effort to get at pi's value. The value of pi cannot be measured exactly. It can only be calculated approximately to any degree of accuracy. This is what Archimedes was trying to do with his calculations, and his method of using polygons was the first rigorous attempt to do so. To get at this elusive value, Archimedes began with a circle and reasoned that if he approximated it with inscribed and circumscribed polygons with ever-increasing sides that have straight edges which he could calculate, he could arrive at a lower and upper value of pi respectively. The ratio of the perimeters of both polygons to the fixed diameter would get closer and closer to the value of pi by narrowing it between two values. Using modern mathematical notation, we will now go through the process he used. To keep things simple and to simplify the geometry, we will focus on the upper right part of the circle. Begin with a circle with a radius of 1 unit. This makes the circle's diameter 2 units. Inscribe it with a hexagon, shown here in red. As a hexagon is made up of 6 equilateral triangles, this means that each side of the hexagon is 1 unit. It also means that the perimeter of the inscribed red hexagon is 6 times 1 equals 6. Now circumscribe the circle with another hexagon, shown here in green. We now find the lengths A and B, which always sum to the radius. The length A is found by the Pythagorean theorem with this expression, where Sn is the length of one of the sides of the nth inscribed polygon. Since A plus B always equals 1, the length B is found by subtracting A from 1. As these polygons are similar, the scale factor of the green circumscribed polygon to the red inscribed polygon is r divided by A. This means we can find the length of each side of the green circumscribed polygon by multiplying the length of one of the sides of the red inscribed polygon by r divided by A. Now that we know the lengths of each side of both polygons, we can now find the perimeters of the polygons by multiplying these lengths by the number of sides. Dividing each of these two perimeters by the circle's diameter of 2 will give us the lower and upper estimates of pi respectively for the hexagons. We now double the number of sides for both the inscribed and circumscribed polygons. This will give us twice the number of sides, and their side lengths will be shorter but not halved. These are the blue lengths shown here, each being the same length by symmetry. This length, which we'll call C, is between points B and C' and is also found by Pythagoras' theorem as follows. This value of C becomes the new value of Sn in the red expression to find A, which then repeats the process. Fortunately, today we can perform these calculations much faster and with greater accuracy with our various technologies than Archimedes ever could. We could simply use a calculator, but because the process is iterative, it is best to use a spreadsheet or a computer programming language. Here is a screenshot of the process done using a spreadsheet. Notice how, as the number of sides doubles, both the inside and outside estimates of pi get closer and closer to it. The last column in blue shows the average of the inside and outside estimates of pi. These average values also converge to pi. This process or algorithm can also be implemented as shown here using the computer programming language Python. If you change r, the radius, to any other positive number, the program will still give the same result for pi. Remember, the ratio of pi is the same regardless of the circle's radius. That's why pi is a constant. Here are the results of running this code with polygons up to 1,572,864 sides. Again, notice how both the inside and outside estimates of pi approach it as the number of sides of the polygons are doubled. Archimedes could only carry out his calculations to 5 iterations with 96-sided polygons and only got the first 2 decimal places of pi correct. For him, the most difficult part of this process was calculating square roots. This piece of code terminates after 19 iterations with over 1.5 million sided polygons and gets the first 10 decimal places of pi correct. All these values are calculated by Python within a second or two. Archimedes' algorithm of inscribed and circumscribed polygons converge relatively quickly to pi using our modern technology. This method of calculating the value of pi using polygons was made obsolete only in the 1660s, when Newton devised an improved method using polynomials derived from calculus. This is the time Newton is referring to when he famously wrote, "I am ashamed to tell you to how many figures I carried out these computations, having no other business at the time." Newton carried out his polynomial calculations to obtain a value of pi to 15 decimal places in the 1660s, while at home during a time of bubonic plague. The final of Archimedes' mathematical achievements is his quadrature of the parabola. In this context, the word quadrature is a Latin word for the process of calculating the area of a 2D shape. This means that Archimedes figured out a way to calculate the area of a parabolic section, the first to do so. This was no mean feat. After all, he did not have the benefit of our modern calculus, which easily finds the area of curved figures such as circles and parabolas. In his work, Quadrature of the Parabola, Archimedes proved that the area of a parabolic section is 4/3 times the area of a corresponding inscribed triangle. He expressed this result as an infinite geometric series with a common ratio of a quarter, as shown here. He arrived at this sum along a similar line to our modern notion of integral calculus. This result is an important milestone in the history of mathematics, as it is an example of the first infinite series to be summed to a finite value. As strange as this seems, this counterintuitive fact forms the foundation of integral calculus. We will show how Archimedes used a very clever mathematical trick to arrive at the result of 4/3. We begin with the infinite sum here. We know from basic arithmetic that multiplying an expression by 1 doesn't change it. Now comes Archimedes' genius. He re-expressed the 1 as 1 minus a quarter divided by 1 minus a quarter. Then multiply the infinite series into the first of the two brackets. When this is done, the result is the following expression, now with two infinite series. At first, this looks worse than the original infinite sum. But if you look carefully, the two sets of fractions cancel because they have opposite signs. Brilliant. We're now left with 1 divided by 1 minus a quarter. This simplifies first to 1 divided by 3/4. And the reciprocal of 3/4 is 4/3. Today, we know there is a formula that finds the sum of an infinite geometric series, and it is this, 1 divided by 1 minus r. With Archimedes' infinite geometric series, we see that the value of r is a quarter. Substituting r equals a quarter, we first get 1 divided by 1 minus a quarter. This simplifies to 1 divided by 3/4. And of course, the result of this is 4/3 as expected. This infinite geometric series can also be coded very easily in Python, as shown here. Here is the result of running this code. We can see that the sum is getting closer and closer to 1.3 recurring, which of course is the decimal expression of 4/3. Finally, we can show the same result of 4/3 using modern-day coordinate geometry, algebra, and calculus. Fear not, the amount of calculus will be kept to a bare minimum. When Archimedes proved his result, he showed that this is correct, no matter how the parabola is sectioned. To make it easier for us, we will only section the parabola perpendicular to its axis of symmetry as shown. Hence, the x-axis will section the parabola. Since a parabola is the result of a quadratic equation, we can generalize this parabola with the quadratic function f of x equals negative k, x minus a, x minus b. Here, the parameter k allows the parabola to be dilated in the vertical direction, while the parameters a and b allow the parabola to be made wider or narrower. The values of k, a, and b are all positive. The x-axis sections the parabola, so we are going to find the area under the parabola and above the x-axis from x equals a to x equals b. The inclusion of these three parameters will show that they make no difference to Archimedes' result of 4/3, as they cancel when the ratio of the area of the parabola to that of the triangle is taken. Here is a triangle inscribed in the sectioned parabola whose area we will now find. To find this triangular area, we need to find the triangle's base and height. The base is easy and is simply b minus a, but the height requires a bit more work. Since the apex of the triangle is at the parabola's turning point TP and the x-coordinate of the TP is always halfway between the x-intercepts, the x-coordinate of the TP is a plus b divided by 2. Substituting this expression for x in the quadratic expression of the parabola, we get the following. This is the expression for the height of the triangle and simplifies to a quarter k times b minus a all squared. We now have everything we need to construct the ratio that will lead to Archimedes' result of 4/3. The ratio of the parabola's area to that of the inscribed triangle's area is this fraction. The numerator is the parabola's area written as an integral. The denominator is the triangle's area with the base and height clearly labelled. This fearsome-looking ratio can be shown to be 4/3 by hand, but you must know how to integrate the numerator and simplify the expression in the denominator. Let's move this ratio to the top of the screen to give us more space. The easiest way to integrate the numerator is to expand the brackets of the integral and then integrate the resulting polynomial term by term. We will leave this as an exercise for you to do. However, we will end this video with the complete solution of this fraction for those who are interested. When the numerator is integrated and the denominator is simplified, the result of each is the following. From this, we can see that the factors of k and b minus a cubed will cancel, just like we said they would. This proves that the height and width of the parabola are immaterial. The result of these cancellations is just 1/6 divided by 1/8. This can be rewritten as a division of two fractions as follows. Then as a multiplication of two fractions as follows. Multiplying the numerators and denominators then results in 8 divided by 6. This then simplifies to 4/3, the very ratio that Archimedes derived. It must be pointed out that Archimedes did not use this exact method to arrive at this result. The method presented here is to give you an appreciation and understanding of his 4/3 result using the modern method of calculus. However, the method he used foreshadowed the concept of what we know today as integral calculus. Archimedes' method in deriving his infinite geometric series that we saw earlier was in effect similar to integral calculus, which involves the summing of an infinite number of terms to give a finite sum. So while Archimedes was not doing integral calculus in the modern sense as we know it, he was using the principles on which the foundations of integral calculus are built on. And all this was almost 2 millennia before our modern notion and notation of calculus were developed. There are also many other things which Archimedes did in the field of mathematics, physics, astronomy, and engineering, which fortunately for us he recorded in his writings. These have survived thanks to the many scribes who valued his writings and copied them throughout the centuries. If you would like to know more about Archimedes, there is a great podcast by the BBC program In Our Time that featured Archimedes on the 25th of January 2007. If you liked this video, then please like, share, subscribe, and add a comment. You can also check out more maths videos at Maths Whenever on YouTube. And for a collection of other mathematical stuff, follow iPhi on Instagram, where I is the imaginary unit, phi is the golden ratio, e is the base of the exponential and natural logarithm functions, and pi is between these two fractions. Thanks, Archimedes. If you're a mathematics student in secondary school and would like to take more control of your learning, then the Maths Factory website is definitely worth checking out. It has a collection of maths videos to help you review a concept and how to use the TI-CAS calculator. Finally, we will close this video with the full derivation of the quadrature of the parabola with the integral, step by step without any technology. Enjoy the algebra and the calculus. Thanks for watching and see you next time.